Okay, now we're going to look at a problem out of the textbook. It's the second problem worked in the section, that's the second example worked in the section on using Castigliano for indeterminate structures. But in fact they give us two methods for indeterminate structures. One is Castigliano, one is a pure strength of materials based linear algebra based method. This problem is on page 179, and this problem is worked using the strength of materials linear algebra method. What I want to do is work this problem using Castigliano's method, and so this will be a mildly difficult problem. Okay, and what was explained in the problem, and you need to read the problem statement very carefully, is that we had a beam on a pivot point, and in fact this is a long bolt that had a nut up top. This was a long bolt connected to ground that had a nut up top, and the nut up top was tightened one turn. When that nut is tightened one turn, it's going to pull this arm down and it's going to put some stretch into this arm. Now, to model this in Castigliano, we're going to change this process by saying, yes, we've got the beam here, we've got this bolt with the nut up top tight. We're going to cut this bolt away from the ground, and then we're going to tighten that nut one turn, and in the process of tightening that nut one turn, it would leave a gap here. Now, since the bolt really is connected to ground, to get the problem into the right orientation, we've got to close this gap by deflecting this structure back down the one thread turn that was taken away up here. In the process of moving this thing back down, we will put the problem into the exact state as described in the textbook. And so what we have is, when we bring this thing back down to the cantilevered end, first of all, there are no bending moments in these cantilevered ends. It's pure axial tension on these cantilevered ends. We're going to have an unknown axial tension force that is required to bring this thing back down and close this gap one thread length. So we're going to use Castigliano in the indeterminate form to calculate the load in this piece that would exist after the turn of the nut by one turn. I'm going to be looking at both sides of the problem. You can see I've labeled X from the left and X from the right. Haven't done that before, so I will show you that. But since I'm going to be looking at both sides of the problem, I need to do the statics on both sides of the problem. And so I need to find my unknown reaction R2, and I actually don't need to find my unknown reaction R1. That one's not necessary, but I'll go ahead and find it anyway. To find my reaction R2, I'm going to sum moments about the pivot point, and summing moments about the pivot point, I've got F acting at a 200 and I've got R2 acting at 150. They're in opposite directions. Set that equal to 0 and solve for R2 is equal to 4F over 3. If I want to find the reaction R1, then I can sum moments about point C if I wish. I'm sorry, R1 is here. If I want to find that moment R1, I can sum moments about point C, and that will involve F and R1. F will have a moment arm of 350. R1 will have a moment arm of 150. So 350F minus 150 R1 equals 0. Gives me R1 is equal to 7F over 3. Okay, now that I know my reactions, and I have replaced my constraint, which is a cantilever from a wall constraint, with its equivalent load F, and this F is redundant. There is no way I could calculate the value of F with pure statics. I can only get it through strength of materials. Now I'm going to look at energies to first calculate the deflection at F in the direction of F. And if I look at the structure, I'm going to have axial tension here, bending here, and axial tension here. And so I need to keep track of all of those energies, and I'm going to have three regions. And so let's look at energies from tension and bending, and I'm going to set my deflection at location F into delta sub t, which in my lingo means the delta of one thread length that's been taken away in the problem. Okay, I'm actually going to divide this into 4 sections. Here, here, the 150 section, and the 800 section. Okay, I want to write my moment in section AB. That's this section, and my moment in section AB at any location given by this x is this force times x. So it's just F times x. And the partial of my moment with respect to F is x. My moment in the region BC, when I make a cut specified by this x, is going to be this reaction times my moment arm, which will be, my moment arm will be x. So it's going to be my R2 times x, but R2 is 4/3 F times x, and the partial of that moment with respect to F is 4x over 3. That takes care of a couple of my terms. Okay. Now we'll deal with our total deflection, and the other 2 terms are going to be pure tension terms. So my deflection at point F is going to be a pure tension deflection on the right hand side, the 800 side, and in this section my tensile force is a constant, and my tensile force was the reaction 4F over 3, and the partial of my tensile force with respect to F is 4/3. And so I've got tensile force, partial of tensile force over AE dx, integrating over that entire 800 length. That gives me my first term. Then my next term, we've got to look at the picture again, is the 150 region. It's the region here, which involves MBC and the partial MBC. 4/3 Fx over 3 is the moment. 4x over 3 is the partial, 1 over EI dx, integrating over the entire length. That gives me my deflection at F due to that term. Coming on the 200 side, it'll be moment times the partial. The moment on the 200 side was F times x, and the partial was just x. So an integral 0 to 200, Fx times x, 1 over EI dx. And then finally, I've got my energy due to axial tension in this 600 section, and my force is a constant, and so my axial tension energy over the 600 length is the force times the partial of the force with respect to F, which is a 1 over AE dx. Those are all of my energies and partials with respect to F, and so that'll give me the deflection of the structure at the place where F is applied in the direction where F is applied. Now, grinding out those terms, let's see, grinding out all of those terms, integrating them with respect to x. And notice I'm going to integrate a constant with respect to x here, constant with respect to x here. These will give me FL over AE type terms. This one has an x squared in it, that one has an x squared in it. I integrate all those terms out, apply the limits, simplify, and here's what I get out of those 4 terms. Now I'm going to take these terms that came out of here, and I'm going to set them equal to my known value of deflection, which is 1 thread length, which numerically in this problem was 1.5 millimeters. So I'm going to have this thing involving F equal to 1.5 millimeters. From that, I can solve for the value of F. If I solve for the value of F, the equation involving delta T, or the delta of 1 thread, is here, and plugging in the numbers gives a force value of almost 3,000 newtons. Now the next interesting question, so remember, what did we do? We replaced our reaction, our support, with an F, with a force F. We use that force F in Castigliano to calculate the deflection caused by that F. But that deflection isn't unknown. We know the deflection. We know that it's supposed to equal this deflection of one thread, which is 1.5 millimeters. So we take our deflection equation from Castigliano, set it equal to the deflection we know. The only unknown remaining in this thing is F. We solve for F's in terms of geometries and deflections, plug in all the numbers, work the units carefully, and we get 3,000 newtons. Now, the next part of the question is, what is the deflection of point A? Okay, point A does not move as far as this point does. This point moves down 1.5 millimeters. Okay, but there's going to be some stretch in this thing. This will move down some, and this will stretch some. Okay, what we'll do now is, knowing the value of F in terms of everything else, we can then apply the load F here and calculate how much point A will deflect. We could do that one of two ways. We can apply our load F at point A and get that deflection, or we could actually just calculate the FL over AE deflection of this rod and subtract that from 1.5 millimeters, and that'll tell us how much A deflects. That's the easier way to do it. We're going to do it the hard way. We're going to take our known F, apply it at point A, and calculate the deflection at point A. And that's on the next page. This thing has been rotated. Let's see if I can view this thing. Rotate view clockwise. Wrong way. View. Rotate view. Well, it'll go counterclockwise. And view. Rotate view counterclockwise. Okay, so this is what I just said. We're going to calculate the deflection at point A because of this load F that we just solved for. Now, the deflection at point A can be solved from the first three terms on our previous page, but we've got to take different, and we are still taking partials with respect to F. So we have the deflection due to this piece, a deflection in that region, and a deflection due to that region. So just copying those terms down, we have, and we're still taking partials with respect to F in this case, because F is the load that we've applied here. So we want to calculate the deflection at A because of the load at F, though. So we only have the three energy terms. We have the 0 to 800 term, that's the axial tension piece. We have the bending piece on the right hand side of the pivot. We have the bending piece on the left hand side of the pivots. And we integrate all of this out, FL over AE, some x squared terms to integrate, no big deal there. We do our integration, we simplify a little bit, we come up with this equation for the deflection at point A, but we know from the previous page that F was equal to almost 3,000 newtons. When we plug in that value of F, and if we're very careful with our units, we get a 0.00138 meters or a 1.38 millimeters of deflection, which means that, and comparing that to the 1.5 deflection caused by the nut, most of the deflection at A, or the deflection at A, is much larger than the extension, than the extension of this member. Point A bends down 1.38 millimeters. We only have about a 0.12 millimeter extension of this piece. Okay, and that's using Castigliano to first of all solve for an unknown redundant force, and then using that redundant force to calculate the deflection at a certain piece within the beam.